Welcome everyone to Newcastle, to Symmetry Newcastle. Our speaker today will be Ciobanu from Heriot-Watt University, and she'll be talking about homomorphisms of free groups and the post correspondence problem.
Well, thank you for the invitation. I'm happy to be here. Well, I will start in a computer science mode, but you'll see very soon how this connects to nice and difficult and deep questions in group theory. So all of this is with Alan Logan and Heriot-Watt, and I must say, it's the lion's share is due to Alan. I mostly am proud to have survived the year of online teaching, so that's my main contribution here. So, all right. So, as I said, the beginning will be about the classical post correspondence problem. I will tell you what it is. It's quite easy, and then and it's also interesting, I think. Then we will talk about this problem in free groups, and we will see that it's pretty much the same statement, but just of course it needs different approaches. But sometimes still we hope that there can be a connection between the computer science and the group theory. This is going to be the third part, which is on some of our results, variations of this problem, connections between the problems, and so on. All right, so to get started, I will tell you about the post correspondence problem. I say it's a famous problem, and it's really taught in every computer science department that has at least some theoretical course. And well, why is it famous? Because it's one of the nicest, easiest to state undecidable problems in mathematics, combinatorics, computer science, and something that we can take and use for other things. And so I will tell you how to see it as an algebraist. Computer scientists very rarely talk about it this way. They use tiles or dominoes and sort of sticking them together. But there's no point in going there when we can just say that we have two algebraic structures. They could be groups or semigroups, and really could be even other, could be rings or algebras, but we're not going to go there. But so imagine if you have two groups, two algebraic structures, so I'll just call them P and Q for now. The equalizer of two maps between these structures. So let's say we have G and H, two homomorphisms or morphisms going from P to Q. And what we're wondering about is the equalizer of G and H. What can we say about that? And that would be all the points in P. So all the points X such that G of X is equal to H of X. So I think the name says quite a lot, right? The equalizer, when are the maps equal? And so this is the first concept to record. And note that maybe if you haven't seen an equalizer, you have definitely seen fixed points of maps. So if one of your maps here, one of the G and H is the identity, and let's say we go from P to P, then what is the equalizer of these two maps, where it's simply the set of fixed points of your map that's not the identity. So all the points in P such that phi of X is equal to X. All right, so everybody has seen this at some point in some context. So what is the post correspondence problem? Well, let's decide what structures do we want to look at. And the classical problem takes two finite alphabets, let's say sigma and delta, and just looks at the free semigroups, semigroups or free monoids rather, but I'll just say semigroups sigma star and delta star, right? So these contain all the words on the two alphabets. And so the post correspondence problem, PCP from now on, to not twist my tongue too much, is given two maps G and H between these two free semigroups. Is the equalizer trivial? Right, so it's not so much about structure, it's just simply the set that we looked at before trivial or not. Now, as I said, if you're allowing free semigroups, it means you have the identity there. So of course, the empty word will be in the equalizer, but that would be a trivial case. If I took the free monoids, then I wouldn't have the identity. So it would be about being empty or not. Now, of course, the post correspondence problem is really a decision problem. So is there an algorithm such that given two morphisms can decide if the equalizer is trivial? But I didn't want to write all of that down. So it's a yes or no question as a decision problem. So let's, I don't know, it's still early here. Maybe not so early for you, but let's see some examples. As I said, it's a very gentle introduction. So take two alphabets, sigma and delta, just two letters each, and take two maps. So this is one map G, this is the other map H. And let's see what happens about the equalizer. Well, note that if you take any, okay, I started with H. All right, so if you take any word, W in the letters Y, Z, what do you get? You really get A, right? For every letter in W, that's going to be a Y or a Z, it gets mapped to A squared. So what do you get is a lot of A's, really, but how many? Well, it's twice the length of W, right? And I don't know why I started with H, but okay, we can look at G. And of course, G of W is also A because everything gets mapped to A, but now we have simply the length of W. So you see that there's never going to be anything interesting in the equalizer. So the answer here, so if we had PCB, the answer here would be no. There is no W, non-empty, that makes these two maps equal. So that would be the first case. And the second case, here we have another G and another H. And so what do we have? For example, we have G of YZ is, of course, AB squared, and it's equal to H of YZ. All right, so the answer is yes. There is a non-trivial word that makes the two maps equal. Okay, so this is what you should be thinking about. And for now, right, we're just looking at words, so that makes it easier. Later on, of course, we'll be looking at groups, so that complicates everything. But yeah, so the Post Correspondence Problem is due to Emil Post. It was published in 1946. It's a very short paper, 4, 5, 6 pages. And what he proved is that, of course, he didn't call it a post, he called it a correspondence problem in free monoids is undecidable. So you cannot decide if there is something making two maps equal. I'm happy this problem is called the Post Correspondence Problem because it has a very interesting and sometimes tragic biography. And he thought about incompleteness and theoretical computational machines before Gödel and Turing, but wasn't able to formalize and publish. And so he gets very little credit in that sense. Unfortunately, there's something named after him that enough people know. So as you can imagine, there will be many, since this is such an old problem by now, there are several proofs. The one that I know, and I can, well, if I had, I don't know, 10, 15 pages and 10, 15 minutes, I could show you, is that you take a Turing machine and the computations of a Turing machine, and you encode that into some maps, which is called an instance of the PCP. And because the halting problem is, well, undecidable, and for Turing machines in general, you will get maps where this is undecidable. So it's a very nice way of playing with the tape and with the instructions of a Turing machine and encode that all to get nice words and maps. Now, if you don't like Turing machines, you can reduce this to other things. So Alan, for example, would encode the word problem for particular, for semigroups and to get the PCB. Of course, now the word problem is the undecidability of the word problem in semigroups does boil down to the halting problem for Turing machines. So, but still, so there's many other proofs. It depends what you're comfortable with and what you want to use as your black box.
Laura?
Yeah. Mm-hmm. Yeah.
So Post wouldn't have reduced to Turing machine? Post had a direct proof?
It was around the time when Turing had published and was, yeah. So I mean, the problem is he saw a lot of these things, but wasn't able to formalize them properly or publish them. But people who knew him, like Martin Davis, was influential in the Hilbert-Stumpf problem, knew that he had all these ideas quite clearly in his mind. I just didn't get to them. Yeah.
Okay.
Right. So why do we like this? Why are we still talking about it? Well, for one thing is that it's nice to teach in a course, even well, maybe not first year, but some course in computer science or maths. And the other reason, that's maybe a better reason, is that it's really the source of a lot of undecidable problems in maths or computer science. So one of my favorite problems that I want to tell you quickly about is the matrix mortality problem, which says that if you take a set S of some matrices, let's say M1 up to MK, so these are, let's say, so this is a set of n by n matrices, and let's say with integer matrices, right? So everything is integer. The question is the zero matrix, how do I write that? A zero like that? I don't know how you write the zero matrix in the best way. That looks funny. So it's a zero matrix in S star, right? So among the products of all these K matrices. And there's a very nice, again, short paper by Alava and Harjou from 2001, which again, I actually given some of my students a project. You can encode PCP into matrix multiplication and or rather into the right, to create the right set and the right setup to get that this is undecidable. So you cannot decide that in that among the products of all these matrices, you'll find the zero matrix. So that's the matrix mortality. There's various versions of this. In fact, the reduction is about deciding if a matrix has a zero in one of the corners. So there's all kinds of things around it, but it's a nice reduction and very quick. Now, possibly more important than this even is the fact that it's a source of a lot of undecidability for formal language theory. I will tell you one thing here that I think is very important. So if you have a context-free grammar, if you don't know what it is, just don't worry about it. But you have some rules, right? You have a grammar and you're getting words. A grammar is called ambiguous if there's many ways to get a word. And if you have a grammar, somebody gives you a grammar, it is undecidable to tell that this grammar is ambiguous, so that there's a unique way for every word or several. And then a lot of other very natural basic questions are undecidable, such that if you have context-free grammars G1 and G2, well, you want to know, is there intersection? So they will generate some languages, LG1 and LG2. Is there intersection empty? Is one containing the other? Is one of them possibly regular? And many other questions. And also there's lots of undecidable results for L languages, which Murray and I love. So, so there's a lot of applications. And again, you could technically always go to the Turing machine, but sometimes it's very hard to see that. And having this easy problem makes it easier to get your result. Right, so is it always undecidable? Well, it depends a bit on the size of the alphabet. Remember, so we were going from sigma star to delta star. And if the starting alphabet has size n, then, well, you can look at some of the small alphabets. And it's, well, when Post proved this, it was, well, there was no bound on how big the alphabet needs to be to get it undecidable. And it was a big result for alphabet of size 7, that it's undecidable. And then, well, since then, we know that for alphabet of size 2 is decidable. It was quite a big deal in 2015 when it was shown that if the alphabet is 5, it's still undecidable. And in the middle here, we still don't know, right? Because you need to sort of push a whole Turing machine with all its instructions and alphabet into small alphabet, and so that's hard. This is what makes these questions hard. Now, something that will be relevant for later on is that if the maps G and H are injective, PCP is still undecidable. So this injectivity will play a big role, as we'll see later. And this is, again, a relatively old result. So I think this is what I wanted to say about the classical PCP. So now let's move on to groups, free groups in particular. So the question that we're asking is very similar. So let's say the Post Correspondence Problem for free groups is the decision problem, which is asking, what is an algorithm such that given two maps between two free groups, finitely generated, can decide if the equalizer is trivial. Okay, so exactly the same statement. We just changed the semigroups into groups here. And I'm still staying with free groups for now, or rather for the whole talk. Right, so the question would be, is this decidable for free groups or undecidable? And yeah, so here the equalizer, again, is we have two homomorphisms between the two free groups, and we're looking at the points that make the two homomorphisms equal. Very easy to show this is a subgroup. Now, of course, as an algebraist, as soon as you have a subgroup, there's questions to ask. Not so much is it empty or not, but is it finitely generated? Right, that would be more natural. And the answer is not in general, and it's not too hard to come with examples. I might say something about this later. So that is not, well, it's fine, but it's if you want to say more about its structure, it gets tricky. However, if one of the maps is injective, then the equalizer is a finitely generated subgroup. Of course, free subgroup, we are inside of free group, so everything is free. So this is a proof of Goldstein and Turner from 1986. There's quite a nice story to it. And maybe I'll say more about this. Was so the topic of equalizers and fixed subgroups was a very major, very hot one in the 70s, 80s, and 90s. And there were a lot of Invenciones paper trying to prove that things are finitely generated or trying to bound the rank of the subgroup. And then they wrote some of those papers, and then they came up with just a 2-page proof of the same thing, which I'm sort of going to show you at the end, depending on time. So it's one of my favorite papers because it's 2 pages and it's got just very clever ideas. And so on MathSciNet, if you read the review of this paper that I hope to get to, the review says the proof uses Nielsen-reduced generators and cancellation arguments expressed in a delightfully simple graphical form. Okay, so that's what I want to show you, the delightfully simple graphical form towards the end. Okay, so, right, so we will stick to one of the maps being injective. I'll tell you what happens if they're not. But see, if we have one of them injective, then it turns out that this kind of PCP related topic was there for a long time. So Stallings asked this in 1984, asked, is the equalizer, well, does it have rank less than the rank of the group? Okay, so without mentioning PCP, or this was about the rank of the equalizer. And also Stallings asked, as anyone would ask really, as soon as you look at these things, is there a basis, or is there an algorithm to compute a basis for the equalizer, again, if it is finitely generated? So these questions are just slightly different from PCP. It's looking for information about the equalizer, not just asking, is it trivial or not? But to us, of course, they make more sense. So what can we say about them? Well, before we say something, let me again bring up the fixed subgroups, right? So if we're sticking to one of the maps being the identity, right, then this equalizer just becomes the fixed subgroup of phi, if phi is your second map, right? So the points where phi of x is x, again, clearly a subgroup. So what do we know about fixed subgroups? So this is where there's a lot to be said. So again, there was something called the Scott conjecture, which asked if the fixed subgroup is of an automorphism to start with is finitely generated, and then is it of rank less than the size of sigma. And there are lots of papers and a lot of people working on especially automorphisms. So I will mention a few names. So Gersten was one of the few to come up with the finite generation. But then the really impactful, influential names here are Besfina, Handel. And because they came up with what we will now call train track maps for automorphisms of free groups. And so this is a topological model for understanding automorphisms of free groups that has been used for a lot of things. And in particular, they were able to show that the fix, so in that paper, in the train track paper, they showed that the rank of the fixed subgroup is smaller than the rank of the ambient free group. And then using the train tracks, many other things were done. And Bobowski Mazakova, they showed that you can compute the basis for this finally generated subgroup. Okay, so now there's a point to be made that for automorphisms, there's a lot of literature. But if you have endomorphisms, there's a lot less known. So there is a result that I need to mention. So again, Imrich, okay, I misspelled this, but fine. Imrich Turner, 89 showed that if I is an endomorph, the same thing holds about the rank. And they just use the Besfina-Handel for automorphisms. So, so that's fine. But then computing anything else about the fixed subgroup has been open since. And so last year, Alan and I were able to show that if we stick to the free subgroup on 2 generators, we can compute a basis for the fixed subgroup. Of course, that sounds quite boring and possibly easy because the basis will have at most 2 elements, right? Since it's less than 2. But it turns out it's still a 35-page paper that is quite difficult. And the reason for all of this is because we don't, well, there is definitely a lot of work happening right now to understand endomorphisms topologically. So to have something like train tracks for endomorphisms, but it's nowhere close to where automorphisms stand. So this was still some very difficult work even for F2. But I don't want to talk about fixed subgroups. I want to get back to PCP, so equalisers. And right, so the question is, can there be some connection between computer science and math? Can we use some ideas from computer science to group theory, or maybe the other way around as well? Right, to go a bit deeper than PCP, to actually look for the basis of the equalizer. Again, one of the maps has to be injective. And if we can't do any of these, are there at least things that we can do, such as restrict the types of maps, right, the G and the H, or look for different variations of the PCP that maybe can enlighten us? And so this is, I'm going to address one or another all these questions. All right, so so this is the now a few results, but also I want to just give you the big picture more than anything. So variations and subcases of the PCP, and what does this mean? Well, so again, PCP is about, is the equalizer trivial? Turns out that, well, we don't know. Okay, so so if one of the maps is injective, maybe let me use a different color. Oops, up to here. So if one of the maps is injective, I'll call this the injective PCP. So one or both, or yeah, something like that. If none of them is injective, like here, I'll call it the non-injective PCP. Well, so it turns out that if the maps are not injective, it's very easy. So if the map is, if none of them is injective, then PCP is decidable. because this set, and I'll get back to the next slide. So this set with consisting of commutators from the kernel of the two maps will be in the equalizer. So let's expand this a little bit. First of all, if you have homomorphisms of free groups, so some people have done this a million times. It's quite easy to decide if they are injective by building, looking at the images on the generators and constructing a graph, and that which we often call core graph, and seeing what the rank is, right? So if you start with let's say 4 generators in a group, you build the core graph, but it has rank 3 instead of 4, then you know your map was not injective. So this is all. I can say more about it. I didn't plan to expand on it, but it's quite easy, very standard to decide that the maps are injective or not. Okay. It's also possible to see, to find some elements in the kernel if they're not injective. So given that, let's look. If you have some elements, right? So remember we have X is in the kernel of G and Y is in the kernel of H. Right, so what happens when you plug in the commutator of X and Y in G? Well, of course you get the G of X is 1, right? And so you get G of Y inverse. Again, G of X is 1 and GY. So of course this is trivial, right? And the same happens for H of the commutator. So you see that we have something in the equalizer that is non-trivial because a commutator, if it's, well, I assume first case is the commutator is non-trivial. If the commutator is trivial, you can see that, right, we're in a free group. So things commute only if they're both powers of the same element. And you can see how you can find the right power of Z, which I'm not going to do now with GCDs and so on, but you will get that that there's something non-trivial in the equalizer. So this is quite easy if they're not injective. You play with the kernels and you can come up with other elements if you want. But what happens in general? Well, in general, it's not the best picture. So, so here I have a table. So these are the problems that I'm looking at for now. And these are free monoids and free groups. So the general PCP, as we saw, is undecidable. I guess we should say post here. In free groups, we don't know. The basis problem, so finding a basis, doesn't work quite as well in free semigroups. Sometimes we want to actually, it's more natural to give the equalizer in terms of an automaton or some other way. And turns out that is undecidable. And I don't have the names here, but yeah, so this has been done. In the free groups, we can call it equalizer problem. So again, we don't know how to compute a basis. And what I just said is if your maps are not injective, none of them is, then it's decidable. Or this is, we just saw this, right? But it stays undecidable for monoids. And when both, or rather one or both maps are injective, this is undecidable in free monoids, and we don't know what happens in free groups. Okay, so everything undecidable here, this is sort of trivially decidable in free groups, and everything else is unknown and open. Now, for some positive results, we will need some good news these days. There are some things we can do. So now I have 2 problems, as I said, variations on PCP, or rather for specific maps, and I'll tell you what these are. And so marked PCP, I'll get to that in a second, but let me start with the generic PCP. So I think many of you, but not all, are used to people thinking about what happens for most maps, right, generically. Also you've seen perhaps enough literature to know that most things are generically easy, right? And that's the same here. So if you are in a free semigroups and you pick, so fix the alphabet, we do fix the alphabet, we're not starting to play with that. But if you fix the alphabets and you're looking at just random maps, you can definitely decide the PCP will be decidable even in polynomial time for most maps, for most pairs. What does most mean? Well, I would need to define. Typically, you look at the images of your maps being random words in a ball of radius n, where you let n go to infinity. So it's something that we've done a lot in group theory for the last 15, 20 years, maybe. So it's decidable. And actually, my interest in PCP was when I was in Barcelona with Armando and Enrique, we were looking at something else, in fact, the Hannah-Neumann conjecture, and we showed that PCP in free groups is decidable for most maps. And I want to tell you just a bit of why that happens, right? So the reason why it happens, again, we fix the groups or semigroups, and the statement is that for most maps, the equalizer is trivial. And so if it's trivial, then you're done with the PCP. Well, why is it trivial? Because, well, it turns out what you're looking at is really, you're looking at the image of G and the image of H, right? Those are going to be two subgroups in your free group. And if you just think of them as K and L, turns out that, and again, given by finitely many generators, which are in a ball of radius n while n gets very large, it turns out the intersection of random subgroups in a free group is just trivial. So there's more to be said there, but I'll just leave it at that. So again, not super interesting, but just something to mention. So that's the generic PCP. Now the marked one needs a couple of definitions. So what is a marked morphism? Well, a set of words, first of all, is marked if every word starts with a different letter. So easy enough, seems a bit artificial, but actually has applications. And so what is a marked set? Well, this one here, right? XY and YXY, they start with different letters, so it's a marked set. So what is a marked morphism? We're sticking to monoids just for now. So a morphism F is marked if the images of the generators form a marked set. So for example, just go with the map from all words on AB to all words on XY. If A goes to XY and B goes to YX, you're looking at the set of images, and that is marked because it's exactly what I started with. So that's what you're looking for. Now for free groups, so why do we care about this? Well, it turns out that looking at these marked morphisms was crucial to proving that PCP on an alphabet of 2 letters is decidable. It was shown that it's decidable in general, in fact, by these 3 authors. And turns out that if you count all the marked morphisms among all morphisms between 2 free subgroups, it's actually a positive, it has a positive density. So it's not a negligible set. They're not just some maps that never appear. It seems like an arbitrary, as I said, artificial condition, but in fact, lots of maps satisfy this condition. Right, so what happens in free groups? In free groups, these things are called, or I guess we took a couple, which is, so we're gonna call them immersions. Which is very loaded work in geometric group theory. Of course, it means different things in different areas, but for now, again, this is what the terminology of Kapovich. So an immersion of a free group is a morphism between free groups where the images of generators and inverses is marked, right? So we can't ignore the inverses because we're in free groups. And so the map that I showed you before for the semigroup is not marked because, so you have XY, YXY, but you see when you take a look at the inverses, you have a Y inverse here and another Y inverse here. And so you're starting with the same letter, which is not allowed. So what is, again, for those of you who are comfortable with core graphs, what is an immersion visually? It's just, if you take, I have a map F here, say f of a is a squared, f of b is bab. When you draw the image, right, as again as a subgroup, this is so you have the identity here of the group, of the free group, and one of the generators is this, right, a squared, and the other one is bab, and so this has no foldings, right? It's all deterministic. You can't put any edge on top of another. It doesn't. So this is, it's as you get it, is as it's gonna stay and be a subgroup of rank 2. And so because there's no foldings, it's an immersion. If you didn't have an immersion, you would have foldings. If you had, for example, the B going this way, then you would fold this edge with that edge, and that would not be an immersion. So just to explain what maps we're talking about, and turns out that for these maps, we can say something. And we were inspired by the computer science paper for marked morphisms of semigroups, really, to work with the free groups. So inspired by the proof, we showed that if we have two maps between free groups that are immersions, so this property about first and last letters, then we can essentially solve the PCP. We very explicitly, we can find what the equalizer is. And we find it as the image of a particular map, which requires discussion and proof. And I'm not going to do that now, but so we can understand or compute the equalizer completely. And so the basis problem, so we understand it as, that means that we know the basis, right, the generators. And by the way, I think if you think for a second, you will see that immersions are definitely injective maps, right? So this equalizer is finally generated. So we can find the basis, and we can also show that the rank of the equalizer is indeed less than the rank of the ambient subgroup that you start with. So yeah, so we worked with core graphs and pullbacks and intersections of subgroups and sort of standard group theory machinery, but I was really inspired from computer science, where they take a pair of maps and get a new pair with smaller complexity, which needs to be properly defined, and go from there. Now, something else I want to show you is a problem that again might seem strange, but it's called the generalized PCP, or GPCP, which I'm stating it for free groups, but actually the way it's done for semigroups, so it's a bit strange. But what happens is you have your two maps like before, G and H, but you also have four words or elements in the free group, U1, U2, V1, V2. And now you're not asking if G of X is equal to H of X, but you're asking if you sandwich them in between these four words like that, does it happen? Is there any X that will do that? Again, why are we looking at that? Because there's applications where you can't just use PCP as it is. You need these extra conditions. So it occurs in lots of applications. In groups, it doesn't make sense to write U1 and V1 here. You can, of course, take the inverse and move it there. But I just wanted, this is how it is written in free semigroups, where you cannot move things around. And it's ultimately, so this could be simplified for groups, but I'm stating it that way just for simplicity. So there's this problem, and that has been studied a lot. And again, it's undecidable when it comes to free monoids, semigroups. It's undecidable along for all things you can imagine. So if you take none of the maps to be injective, it's undecidable. If you take one to be injective, at least then it's undecidable. So everything undecidable. Now for free groups, and this is a paper where the first paper to study them, PCP and GPCP in an organized fashion. So from 2014, Myastikov, Nikolaev, and Ushakov showed that it's undecidable. And when you look at their proof, it turns out the maps they're using are both non-injective. So in fact, when at least one map is injective, we still don't know. And so there's something else to be said about this paper, is that they're looking at all these problems, not just for free groups, but for nilpotent groups and a lot of other classes. And also something to be said is that GPCP on alphabet of 2 letters is decidable. So for free monoids, but that's the only decidability we have. Okay, so this is the big picture. Now let's see what connections can we make, coming back to free groups basics. So if you have, again, let's say, so you have the maps G and H, and one of them is injective, let's say G injective. Then you can talk, right, about the equalizer being finitely generated otherwise. Okay. So if you have this setup, then you can ask what is the basis for the equalizer. Obviously, if you know a basis, you know what the rank of the equalizer is. You just read how many elements you have in a basis. Now, if you know how many elements you have, remember PCP, sorry, you haven't seen this notation. I just want to make it shorter. So PCP ing means just PCP where, right, the injective version where at least one map is injective. So, which is what we have here really. So if you know the rank of your equalizer, of course, you know if the equalizer is empty or not. And notice that GPCP, I didn't say that, it's just a more general, well, it gives you, if you know how to do that, you immediately know how to do PCP, right? Because you had U1 GX U2 equals V1 H of X V2, but for right U1 U2 V1 V2 trivial, of course you get PCP. Okay, so these are obvious things you can say. Of course, you can solve PCP for all maps. You can solve PCP for injective maps. But notice that if the maps are not injective, remember we said we can trivially solve things with that discussion about kernels and so on. So in fact, really, this is a if and only if, right? So what else can we say that would be new and interesting? So there's quite a few connections we made. I'll just show you two of them. So one is that if you know how to find the basis, well, you can definitely find, say something on PCP, but you can in fact say something about the GPCP, which is not obvious, right? So we're actually getting a connection this way. Okay, so that's something that takes a bit of work, but not very much. But something else you can say that in fact, the basis and the rank problem are equivalent. So again, it's very obvious that if you know a basis, you get the rank, but turns out that the other way around also works. So I want to tell you now, let's see, I have about 10 minutes. So I want to tell you a bit about this because it involves the delightfully, if you remember, graphical form proof of Goldstein and Turner. So, right, so we want to show that computing a basis for a subgroup, in this case, we'll talk about the equalizer, is the same as knowing the rank. And again, one direction is obvious. The question is, how do we go this way? Right, so we assume that know the rank, right? So we're going to go this way. We assume we know the rank of the equalizer. We need to assume that G is injective, otherwise the rank is infinite or might be infinite. And we want to find the basis for the equalizer using the Goldstein-Turner approach and graph. So something that, okay, not so exciting, but we need to translate the problem from equalizers to fixed subgroups. It can be done with a few maps. So if G is injective, you know that when you go from when you go from the group to just the image, of course, becomes injective as surjective, therefore an isomorphism. And so you can take the inverse of G from the image to the free group. And the point is that by looking at G inverse and then H, you get this map. And yeah, I think it's very hard to follow in a talk like this, but the point is we can, these two things will be isomorphic, and we're going to look at the fixed subgroup of this map defined on the image of G. So not the initial free group, but still a free group or free subgroup. So just a preliminary translation of questions. Okay, so that's the map to look at, and it's very easy to show that this has a fixed point y if and only if H and G have point X in the equalizer, which is simply such that G of X is Y. So I think if you write it down, it will be clear, but seeing me draw arrows probably not so helpful. So anyway, the point is we have a map which goes from a subgroup of the free group into F. How do we think of fixed subgroups now? So that's the interesting part. So we note the rank of the fixed subgroup and we want to compute a basis for it, right? So this is what Gaussian and Turner called, built a graph, which they call d phi, that's attached to this map phi going from a subgroup generated by some elements alpha 1 to alpha k into F. Okay, so what is this graph? So the Gaussian and Turner graph. Well, the vertices are all of the free group, and you put an edge between two vertices, which you label by one of the generators alpha I, if V is phi of alpha I times U times alpha I inverse. So now if we were in a room, I would ask you, what is that? What is that relation? Well, this is saying that U and V are twisted conjugate by a generator of H. Okay, that's exactly twisted conjugacy, if you're familiar with that. If not, it's absolutely no problem. And so, right, so this is essentially if, so U and V are phi twisted conjugate. And so what happens now, so you're building this graph, it might be disconnected, but what happens if you have a loop? So first of all, you'll definitely have the identity element, right? Sometimes I write epsilon because I think of a semigroup, but I should maybe write a 1, I don't know. So what happens if you have a loop in this graph? Right, so you started the identity, in particular the identity, you started the identity and you have an edge alpha, say I just picked some random elements, alpha 2. What is this vertex here? Well, if you look at the definition, it's essentially phi of alpha 2 times the empty element times alpha 2 inverse. What is this guy here? It's going to be phi of alpha 1 and whatever we had before, and so on, right? So as you go around, since this is a loop, what are you going to get at the end? You're going to get essentially that the empty word, right, or the identity at the very end is actually phi of whatever label you had on the loop, right, which is, well, okay, alpha 2, alpha 1, it doesn't matter, your word times exactly the same word inverse. And so what does this mean? Well, this is equivalent, of course, to the word being a fixed point. Right? So phi of alpha 2, alpha 1, alpha 3, alpha 1, alpha 2 inverse is the same thing. So you notice that the loops in this graph are exactly the fixed points of the map you started with. So this is a nice idea, and if you look at now the component that contains the identity, as there might be lots of components, right? You can remove all the others, right? So here I made it looks like a bug of some sort. So you have one component here. So you remove all the other ones and you just keep the ones you have. And actually for what we're doing later, we're going to remove the vertex, the degree 1 vertices to get what we call a core graph. But the point is that the fundamental group of this graph is exactly the fixed subgroup phi. Right, I showed you that the loops are really fixed points and they will generate everything. So this is a very nice idea. And what Goldstein and Turner prove is that if your subgroup H is given by a Nielsen reduced basis, then you can orient this graph, this one here, such that all but finitely many vertices have less than one outgoing edge. So if that can be done, then pi of gamma phi is finitely generated. So I think I mashed two things into one. Actually, they showed two propositions. One is that if you can orient a graph like that, then the fundamental group is finitely generated. And two, they showed that if you start with a Nielsen reduced basis, you can orient it. But that's a very nice combinatorial trick. And as I said, 2 pages. It's sort of overriding all the lots of papers before that on finite generation. So we use this approach, but I'm getting close to the end. We use this graph by knowing what the rank is, right? We are able to construct the graph by starting with the identity and adding a vertex at a time, using the particular way you build edges, and always checking the relation that I think we all know, right? Fundamental groups of graphs, number of edges minus number of vertices, the rank of the graph minus 1. So there's a lot more to say there, but the point is that knowing the rank, we can build the graph itself. And of course, if you know the graph, then you can know the basis. So that was a bit rushed, but hopefully I gave you a bit of the picture. So some of the new connections we have is that basis or rank, pretty much the same. But I mean, the reduction is not a nice polynomial reduction. It's not, complexities are not good, but we just started, so we'll see. So, but then the rank implies the stronger form of GPCP, and that always implies the PCP. And now I think I'm at the end. The problems that I talked about are still undecidable the problems that I talked about for free monoids have been undecidable for a very long time. And their injective versions are undecidable. So everything is bad for free monoids. GCPCP is undecidable for free groups. This was the paper of Myasnikov, Ushakov, and so on. But when you look at their paper, the maps that they use are non-injective. So in general, PCP, GPCP stallings, rank problem remain open. And we showed that the basis and the rank problem are equivalent. We got a few nice implications, but well, there's obviously a lot more to be done. And I have finished. Thank you very much.
Thank you, Laura, for the talk. Are there any questions?
Maybe I have a small comment on the beginning. Well, you mentioned the mortality problem for the matrices. You quoted the paper of Hariu and Halava, but actually, well, it's a paper in American Mathematics that we actually make the popular introduction to the topic, but the actual proof is back to 70s, so it's quite old.
No.
But,
no.
Actually, they say that the proof they present in their paper is due to Watterson, but the funny thing is, well, it's quite an interesting problem. Well, for dimension 2, so if we have matrices of size 2 by 2, people don't know how to solve this problem. So we have a set of matrices, and well, they're not invertible, of course, because we want to express a zero matrix as a product of them. So we have matrices with integer coefficients, size 2 by 2, and people don't know whether there exists an algorithm, whether one can find a zero in this submonoid generated by these matrices or not. Well, that's just an interesting problem I wanted to mention.
There's a lot of...
for 2 matrices. I think even for 2 matrices, people cannot do it.
There's a lot of literature. I didn't want to go there on the size, right? On the it's already undecidable for 3 by 3 matrices, but then there's a lot to be said about how big your set of matrices, and there's a lot of still ongoing research on that, and
Okay, I think Murray wanted to ask something.
Yeah, I wanted to ask if you and Alan had thought about the rank of solution set to a system of equations. Or is this going to help with anything?
I don't think this is related. No. No,
Okay.
we have thought, but no, this is definitely different. Yeah, I mean, so there are people who wrote, I mean, there's people like Pedro Silva and others who wrote, and actually also about hyperbolic groups, maybe. I will say the wrong name, so I shouldn't. But they're looking at the equalizer as a language, looking at infinite points, sort of a ray, an equalizing ray rather, of a map, and things like that. So there's connections in that sense to languages. There's quite a few things, but yeah.
The PCP is kind of the opposite of solving an equation. So in an equation, you're given an equation and you're trying to find a solution. With this, it's almost like you're given a solution and you're trying to find the equation. Like the equation is X and the solutions are G and H. So it's almost like the opposite.
So it's a connection. It feels like a strong connection, but backwards.
Well, yeah, but it's but you can like it's a meaningful connection that you can't do anything with.
Okay.
Do we have
because
any
if we
further questions? Or sorry, Mario, you're going.
Well, if we have a system of equation and we solve it, and we, here's the solution set. Can we then do, we have this solution set together with the original equations. I mean, can we somehow frame that as one of these post things and calculate the rank of the solution set? I'm sure not, but.
Yeah, so they always felt quite orthogonal, yeah.
Okay.
But unfortunately, but who knows, yeah, maybe.
Cool.
All right. Do we have any further questions for Laura? Well, doesn't seem like it, so let's thank our speaker one more time.
Thank you.
And yeah, we will be back in 2 weeks, hopefully. So thanks everyone for coming.